Okay, so the thing that I want you guys to recognize, like my goal for this lecture, is for all of you to see that F net equals ma and torque net equals I alpha. These two equations are equivalent to each other. The thing to know, this is what you use if you're dealing with a linear situation. If you have forces acting on an object, like that block of wood right there. If I exert a net force on that block of wood sitting right there, what's going to happen to it? It'll have a what? A net force causes a what? A net force causes a linear acceleration. Now, what if the situation you're dealing with is not a linear situation? Like say you're looking at a wheel, like that wheel I have on that stand right there. What if you have a situation where a net torque is applied? If you have a net torque, what is a net torque going to cause? An angular acceleration. Okay, so let's just look at these equations. So the analogy goes like this, or the connection is this. Net force is for linear situations. It becomes net torque if you're dealing with a rotational situation. Now, what is mass a measure of? Inertia. But if you're dealing with a rotational situation, the mass becomes rotational inertia, which is also referred to as moment of inertia. Okay? And then our linear acceleration becomes angular acceleration. So these two equations are very, very similar. They're equivalent to each other. All right? Now, let's just look at two situations. I have two situations here. So guys, if the mass of this object right here is 3.5 kilograms, what would the acceleration be? So you're good enough at physics now where you could probably do that in your head. So we have 10 newtons to the right, 3 newtons to the left. The mass of the object is 3.5 kilograms. What would the acceleration be? The acceleration here would be 2. Right? Now, how did I figure that out? What's the net force for this situation? Well, 10 to the right, 3 to the left. What does that simplify to? 7 newtons to the right. If the mass is 3.5, so you take so acceleration is going to be F net divided by mass. So the net force is 7. The mass of the block is 3.5. So this gives 2 meters per second squared, right? Now, come down here. So here, let's say I told you that the radius, so this is the axis right here. It's like a wheel on an axis. We have an axis. Let's say that this radius is 0.5 meters on both sides. All right? What would be the net torque here? Let's solve for net torque for this situation. And by the way, is this wheel here, is this wheel going to stay at rest or what? What would happen to this wheel?
Spin.
It's going to not just spin, but it's going to accelerate. Like, so the way you can think about this, pretend these forces are created by masses. You have these masses hanging here. That wheel would not just spin, but it would accelerate. And the reason I know that it would accelerate is because we have a net torque. Okay, so how do we figure out the net torque? Well, remember, what's the basic equation for torque? Which you now already know. Torque equals force times lever arm. And the key thing when you use this equation, the force and the lever arm must be perpendicular. Okay, so if the radius of this wheel is 0.5 meters, what's the torque from this force here? It'd be 1.5 Newton meter, right? Because you go force times distance from the axis. That's the lever arm, and they're perpendicular. So 3 times 0.5 is 1.5. Okay, what would be the torque from this force right here? So force multiplied by distance from the axis, which is 0.5. What would this torque be? 5. Now, do these torques agree or do these torques disagree? They disagree, because this guy is trying to rotate the wheel clockwise, whereas this guy is trying to rotate counterclockwise. The sign convention for torque is clockwise, counterclockwise. So what would the net torque be for this wheel? So we have 5 Newton meters clockwise, 1.5 Newton meters counterclockwise. What would that simplify to? 3.5 Newton times meter. Now, if you knew what the rotational inertia was, then you could solve for the angular acceleration, right? If you knew what the rotational inertia was, you'd be like, okay, the torque net is 3.5. I know the rotational inertia, right? And then solve for angular acceleration. So dudes, does everybody see the connection between these equations? F net equal MA, F net equal to MA is equivalent to torque net equals I alpha. Okay? All right, the problem we're going to do tomorrow is this. Okay? So if you look at this situation, you know, you're going to see there's a net torque on this spool. What's the net torque being caused by? Well, we have a bucket hanging here. There's a tension in the rope. So we're going to start class tomorrow with this, but I want to show you guys something in class. Let me wrap the video here.